Hi, welcome to our second virtual Linux lecture. Today we're going to cover a topic that you have actually covered in a lot of details. So it's going to be just the difference or some of the main highlights, trying to shed light on some of the things that are very unique to Linux memory management. Uh, Linux I mean, not just Linux, but lots of operating systems share a lot of ideas and how they do memory management. And in fact, uh, almost not almost, but many of the concepts that you should have studied in your undergrad operating systems course uh, actually is reflected into the Linux design and into how the Linux is handles memory. So with that in mind, we'll just work on basically looking into some of the different aspects of Linux. Again, I hope that you guys are social distancing, sitting at home, I don't know, having popcorn or doing something, bringing a series or something. And I hope that you and your entire families are doing well. So in this lecture, we will talk about three different parts into the Linux memory management subsystem. The first one is how the system does kernel memory allocations. The second one is user space memory management, and the third one is caching in memory. So before we start, we should take a look at some numbers that every programmer should know. You should basically always think when you're reading and writing data, I mean, that is regardless if you're doing that in the kernel or somewhere else, about where will your data end up to be. You should not never make assumptions on where it will be, but you should rather think about where it can be. So basically, if you're fetching data from a server in Europe, that's typically 150 milliseconds away from you for each packet, basically. Okay, so if you're sending and receiving lots of packets, you have to factor this into how your system will work. This is now important if you're building a highly responsive server, while thinking about, okay, maybe some parts of my service can go into scripts or something that can run on user side. Some parts of my code will run on the server side. Maybe I should utilize the CDN that is closer to the user in Europe, and so on. Then you have also a time factor when you're trying to fetch 1 megabyte sequentially from disk. And basically, from disk, these numbers are not for an SSD, they are for an HDD. Obviously, you can do way better now with an SSD, but still, there is a significant delay when it comes to fetching data from disk, even seeking data from disk, so where the data will end up. Because you remember your hardware class, you basically have a spinning motor that actually needs to physically move to go to the correct sector, for example, in an HDD. Now you have much shorter performance penalty when you go to memory, around 250,000 in nanoseconds. And you might be thinking that, okay, why are we talking in nanoseconds now? Because basically your fastest thing is fetching data from the L1 cache, and this takes around half a nanosecond. These numbers do change year by year, but the hierarchy of memory is still the same. In fact, in many cases, when you get what is called now software bloat in both the software size and the software performance. Basically, you have the hardware doing this amazing, great strides to make the hardware very fast, and in the opposite side, you find software that is doing stupid things to make that makes the entire system feel like it's something from the 1980s. I'll give you my favorite example. Windows 10 is actually one of the worst pieces of software that I can think of, and many people would disagree with me, but basically the idea that in Windows 10 you have this mechanism that they came up with that accesses disk very frequently, making the entire operating system very sluggish. I mean, I just bought a machine for my wife, and basically the performance there was way worse than a machine that I have that I've had for 12 years old. And it's not an issue with the hardware. The hardware is fine. It's an issue with how the system was designed. It accesses disk way too many times. I actually had to go and buy an SSD, which I mean, I never knew that this would be the case, because I've been running on Linux for quite a while. And now the performance is way better because SSDs are way faster. But yet again, why do I build a system that accesses the hard disk that frequently, thinking that this is a way to actually make your system more performant? And the worst part of it, I can't remember what was that feature, but I tried to disable it like 5, 6, 7 different ways. I could not. Maybe I do not know anything about Windows, but maybe also the programmer has thought that, oh, new brand new hardware, very fast, let me just access this like crazy. Everybody is going to get an SSD. Okay, but still your performance is way worse than running on in an old Linux machine. It was actually slower than my mobile phone. So when we talk about these things, we should always think about what costs are we introducing in our software. And this is especially important if you're writing server-side code, for example. So if you're building a web service and you start accessing disk way too many times, you're going to screw up performance. If you're writing a database and you're trying to access disk way too many times, again, performance will get hurt badly, and so on. So you want your system to be performant, and typically doing that requires you to actually understand these trade-offs between the different numbers. So Colin Scott has been actually calculating. A guy from Berkeley has been fetching these numbers yearly. He has the numbers for 2020 in this link, and you can actually look at these performance numbers with how do they change each year in that link. Okay, so now that we have established that that basically accessing memory is way better than accessing disk. Obviously, accessing the processor cache is even much better, but the processor cache is a very scarce resource, typically very small, so you cannot really put so much into it. So most of your program data will end up in memory anyways, right? So now we need to think about what is the memory access pattern for 3 different parts of the kernel, right? The first one is basically the kernel itself trying to allocate memory to its own processes. The second part is basically when there's an application that requires memory. And the third part is basically if the kernel can build internal caches to make to basically mask accessing the disk. We'll talk about disk I/O in the next lecture in Linux. So kernel memory allocation, all processes that exist would require memory. Actually, one definition of a process is that it's memory. It's some memory locations that are assigned with some code that runs on and manipulates this memory. Very few, if any. I don't think that there are any programs that you can write without having allocated memory. That includes the kernel. So all processes, all subsystems require memory allocation. Now the huge difference between when you allocate memory in the kernel and when you do that in user space is that the kernel cannot easily deal with memory allocation errors. So I mean, if you end up corrupting some data, the kernel would happily shoot itself in the head if you decide to do so, because wow, you are the master, you're the programmer, right? And in many cases, the kernel often cannot sleep. So some parts of the kernel will not sleep. Some kernel threads will sleep, but the kernel itself will not sleep. So there are a few differences between the kernel memory allocation and how user space allocation occurs. The kernel treats physical pages as the basic unit of memory management. Again, pages as very similar to what we have been discussing. The x86 processors include the hardware memory management unit that you have talked about in the Linux lecture. And memory management in Linux is way more complex than how it is managed in Linux, as we will shortly see. Okay. One huge reason of this variability or of this complication is that you're trying to basically support everything from a mobile phone to a microcontroller to a supercomputer. So you need this, and each one of them has vastly different memory architectures. So I mean, how do you actually support all this with a general kernel code? So now that we have talked about pages, this is actually a slight detour of how the kernel does the allocation internally for the kernel processes. Let us take a look at basically pages in Linux. So you have basically studied in the Linux lectures that pages has a default size of 4 kilobytes, and this was the case in the kernel. Okay, but since version 2.6.3, the kernel started supporting something that is called huge pages, along with the 4 kilobyte pages, and the rationale was quite simple. On a machine basically with 8 pages with the full size is 4 kilobyte, were in the days of the 32-bit processors. 64-bit processors have 8 kilobyte pages. Okay, but pre 2.6.3, 4 kilobyte pages were the norm. So on a machine with 8 kilobyte pages and 32 gigabytes of memory, physical memory would be divided into around 4,200,000 distinct pages. On a 64-bit Linux, okay, you can have up to 128 terabytes of virtual address space and up to 64 terabytes of physical memory. So you see, when systems were in the 32-bit space, it was pretty normal to basically have something in the order of 4 million pages, while when you go to 64-bit Linux, you can have up to 64 terabytes of physical memory attached to your machine. So now if you try doing your calculations, you'll find that you will have an enormous number of pages that you need to access and to search and to manage. Okay, so assigning memory is relatively cheap. You basically say that, okay, page number X with this memory walk, with this memory tree pattern, should go to this physical page. However, the management itself is very expensive because every memory access requires a page walk. You actually try to find it using the page tables and so on, and segmentation and the segmentation structure that exists and so on. And then it typically takes 10 to 100 CPU cycles to actually do a single page walk. Okay, so now you have something like 4,200,000 distinct pages. If you're accessing all these 4 million pages, so you're running at high memory utilization, then you can see how many CPU cycles you'll be wasting when you try to access these. Okay. In addition, one of the optimizations that we had was the TLB, and a TLB can typically hold up to 1024 entries. It's actually a very expensive piece of hardware to add to the processor. this is basically out of 4 million distinct pages above. 8 kilobyte pages, 64-bit processor, and 32 gigabyte of memory is actually quite common even in laptops today. So I mean, we're talking about really not a very high-end setup. So every time you can store up to 1000 pages, 1024 pages and page addresses in the TLB, out of 4 million distinct pages. Okay, so, and every time you have a context switch, you will need to flush your TLB, and flushing, as you know, has quite a high cost when it comes to basically wasting resources, because because then you will need to reload your TLB and so on and so forth. So it is actually quite expensive to manage very large memory systems when it comes to the management overhead. Also, there are many large memory applications that exist today. Okay, it's very typical that you will get a database. This is actually from these numbers are for an Oracle database where you have 17 gig of data and 1000 connections basically happening on the database, right? It's an online database basically. Okay, this would use approximately 4.4 million pages, our entire 64 gigabytes roughly, and the page size, the page table size will be 16 gig. Having larger page sizes might enable us to significantly reduce memory walks for such an application if we basically can, for example, have maybe 2 megabyte pages, right? And then each table can fit or many of the tables will be able to fit in a single page, or maybe have larger pages, and then you can fit a single table in a page, and then your memory walks will be much less because now page sizes are much larger, which means that if your page size is 1 gigabyte, for example, and you're using 16, then you can have 16 pages basically for the entire application. So you're not going to go back and forth. Now, this is the idea behind huge pages. On x86 processors now, it is possible to map 2 megabyte and even 1 gigabyte pages using entries in the second and the third level page tables. Just the page tables that you have studied in your undergrad class and that you have studied in your Minix class. Your third level pages and your second level pages in the table can be that large, right? And in that case, these pages are called huge pages. The idea is that using huge pages will significantly reduce the pressure on the TLB, improving the TLB heat rate and thus improving the overall system performance. So now, if you have only 16 pages, right, in our previous example, and you take these 16 pages and put them in the TLB, you can fit the entire 16 pages in the TLB, right? In fact, you have more than 16 because this would be your second and third level page tables. So it allows power users to choose the correct page size for their application. So if you know that your application can make use of 1 gigabyte pages, then use it. However, it causes fragmentation in the memory because now it's so the idea of having smaller pages that you can fit the page anywhere when you have empty blocks in your memory, in your physical memory. But now all of a sudden you cannot do that because you have these huge pages if you that wouldn't fit anywhere. So this is how a system with huge pages will typically look like. Okay, you'll have a mixture of basically normal pages and huge pages. And you typically, I mean, because you have, you're not going to run only on huge pages, because you have all your kernel processes that are running and they do not need 2 megabytes, so 2 megabyte pages. You have multiple applications that are actually optimized on the 4K memory sizes, the 4K page sizes. So you'll have a mix of both, and this is how Linux can operate today. Now, previously, you were instructed to actually start to actually define the huge pages yourself, okay, and assign them to the applications yourself. As I said, a power user. So again, in a later Linux version, they came up with the idea of transparent huge pages, THB. And this builds on the above concept and is the default for all applications today. So you no longer need to actually do this assignment by hand, as was the case in version 2.6.3. But the idea is that if an application asks for a large memory chunk, give it a huge page instead of a small one. So if your application comes in and says, I need 2 megabytes of memory, so instead of assigning it 500 pages, you're just assigning it one page with 2 megabytes. Okay, and on this way, you can actually do this transparently. Now, this is enabled by default in your Linux system. However, you need to actually instruct it to enable huge pages to work. Okay, so you need to actually do some kernel configuration, very simple command line configuration that you can actually look up on the internet to actually enable. It's enabled by default for all applications, but to actually make applications make use of this, or make the kernel make use of this. So this is an optimization that was introduced in the kernel. So is it any good? Okay. Now, lots of people hate it. Okay. Actually, one of the main applications that people viewed will use these huge pages, which are Oracle databases. They actually have even links that instruct people to disable them because it improves performance. Because the application has some optimizations, the database has some optimizations that depend on the 4 KB or 8 KB size of a page. However, many others say that this is basically because the application developers are locked into their old way of thinking. You can actually get a lot of performance gains, maybe 10, 15, sometimes more percentage, by just using huge pages. So the first link discusses some of these gains. The second link basically tells you, please stop huge pages. The third link actually discusses huge pages and in some more details. One thing to note is that many of today's modern or research-based applications, they run on something that is called DPDK. I'm not going to go into deep in the DPDK system, and many of them actually require you to use huge pages for them to work. Okay, so now this is a research problem if you are interested into how to into operating systems research. So we go back to memory in the kernel and discuss it in more details now. So back to memory in the kernel, right? Now, the kernel does not use huge pages. I just thought that this is time to introduce huge pages because we're talking about pages now in the Linux kernel. The kernel actually uses the normal size pages. And the kernel represents every physical page on the system with a struct page, okay, structure. This is defined in mmtypes.h, and the kernel has no way to track which tasks are using a page. It's actually the struct pages. If you're reading from the book, the Robert Love book, you'll find a much simpler definition than what exists today in the actual Linux code. So basically, knowing that this is where the structure exists, and you can look at the documentation for the structure. It's actually pretty well documented. The page structure is associated with physical pages, not virtual pages. This is something that you should understand, that now we're talking about physical pages and not virtual pages. And basically, since you have this struct for each physical page, you can end up actually with just the combination of these page structures for a large memory system can well exceed 100 megabytes. So just the structure that describes the each page. Okay. And one of the important things that you should understand in the struct page is the page flags. The flags field stores the status of the page. These would include things such as, is this page dirty, or if it is locked in memory. Now, locking, we understand. What is a dirty page in memory? As we'll discuss later, you can actually use when you use your memory as a cache for your disk, you actually can dirty memory pages while not writing back to the disk. So there are multiple occasions where you actually write to the memory, and your memory is not stored anywhere else. So that's how the page becomes dirty. There are at least 32 different flags that are simultaneously available to control or to actually to describe each page. So there are various options for you to choose. And also a second thing that the struct contains is a method for the or a variable for some variables for the kernel to track the pages and track how the pages are changing. One of these variables is the underscore count field, which stores the usage count of the page. That is basically how many references there are to this page, how many applications are using this page, how many threads are using this page, how many tasks are using this page. This is the way that the memory subsystem in the kernel would actually remove a page once no one else is trying to access it. When this count reaches -1, no one is using the page, and it becomes available for use in a new allocation. So you basically, this is how you know that, well, this memory page is no longer needed by any other application, or by any other application. I should be basically repurposing it for anything. The virtual field in the page's virtual address is the page's virtual address. So you can, this is yet another way for the kernel to do the mapping between physical pages, which are described in the struct page, and their virtual address space. And now the kernel also needs to know who owns the page. Possible owners include user space processes, kernel data, so it's a page that the kernel owns, kernel code, page cache, and so on. So this is another thing that the kernel, this is another field that exists in the struct page. Memory zones. Because of hardware limitations, the kernel cannot treat all pages as identical, right? Some pages will sorry. So there are many different kinds of pages. Okay, so the kernel basically divides pages into different zones, basically saying that this is page of type A, or in zone A, this pages are of type B, so they go in zone B. The kernel uses zones basically to group pages that are similar in some ways. This is basically because the kernel needs to deal with lots of different hardware with different memory addressing schemas. So some hardware devices can perform DMA, direct memory access, to only certain memory addresses. Others, some architectures, can physically do DMA to larger amounts of memory, and they can actually access almost anything using DMA. So these differences in the indirect memory access is basically the ability of a device to access memory directly rather than going through the processor. So this basically makes it of paramount importance that the kernel covers for all different hardware types, covers for all different page properties that can exist. So the zones, the kernel zones are defined mmzone.h, and this is a link to that file. And there are 4 main kernel zones. Okay, I need to basically say that the actual use and layout of the memory zone is highly architecture dependent, and not all zones need to exist for all architectures. We'll talk about this in a few seconds. So each zone is represented by struct zone that is defined in the mmzone.h file that I just put a reference to. And this zone contains and these 4 zones are either zone underscore DMA, zone underscore DMA 32, zone normal, and zone high mem. Zone underscore DMA, this zone contains pages that can undergo DMA. So pages that have direct memory access enabled. So multiple devices can access them using direct memory access. Zone DMA 32 is a similar zone, but is accessible only by 32-bit devices. So maybe you have 64-bit devices on your computer, and 32-bit devices. The zone contains pages that only support 32-bit devices. Now, as I said, depending on the architecture, depending on what you have in your computer, where a computer is a much more general definition than your laptop, you might have zone DMA or zone underscore DMA 32. So if all your DMA enabled devices are 64-bit, then you will not have the zone DMA 32. Similarly, if all of them are 32-bit devices, then you will not have the zone underscore DMA. Then the third one is zone normal, and this zone contains normal regularly mapped pages. And zone high mem contains the high memory, which are pages not permanently mapped into the kernel space. Basically, on a 32-bit processor, zone high mem, x86 system basically, or processor in general, zone high mem will be all memory above the physical 896 megabytes. So if you have a 32-bit processor, and that 32-bit processor basically has an attachment of 8 gigabytes of memory. Okay, 4 gigabytes of memory, 2 gigabytes of memory. Anything above the 896 megabyte mark of physical memory will go into the zone high mem. If you have a 64-bit processor, x86 processor, then zone high mem does not even make sense. So is empty because all memory will be directly mapped. So normal high mem are basically if you have direct memory mapping, okay, or indirect memory mapping. So it's actually important to understand that for example, most x86 64-bit processors today, you'll probably have only two zones used, which is zone underscore DMA and zone underscore normal, because the high mem is not needed and the DMA32 is not needed. So how does the kernel allocate pages internally? These are the methods that the kernel uses to allocate internal memory. Alloc underscore page. This would allocate a single page, a single memory page. Alloc underscore pages, and this will allocate multiple pages. Get free page allocates a single page and returns a pointer to its logical address. Get free pages again allocates 2 to the power of order pages and returns a pointer to the first logical address. Get zero page will give you a page that has all zeros, okay, and returns a pointer to its logical address. If you look at all this, they either take one parameter or two inputs, basically. The GFP mask we'll talk about very shortly, and the order. The order is basically you allocate pages in order of twos. So you either allocate one page, 2 to the power 0, okay, you allocate 2 pages, 4 pages, 8 pages, 16 pages, and so on, okay. So this is how. Now if you want to allocate 3 pages, then you do alloc pages order 1 and you do an alloc page right after that. Now you have your 3 pages, different pointers, but it is what it is, okay. So basically this is the way that the kernel internally uses to allocate memory pages. What is the GFP mask? Well, there are multiple things that you can ask of a page, okay. One of them is that you can basically control, for example, if that page is allocated in different zones, for example. So if it's normal, if it's in the normal zone, then you do not need to specify. But if you want it in the DMA or DMA32 or the high mem zones, you actually need to specify it by the flags that are towards the bottom. Now, you can also control the how the allocator actually works. For example, can the allocator sleep while trying to allocate the pages to you? Can the allocator basically access the high the emergency pool of, and we'll talk a little bit about that, of memory? Can the allocator start disk IO? So if it fails to basically allocate a page, should it basically start swapping? Can it start the file system? Can't use cold pages, so pages that have not been used previously. Should it print you a warning if it fails? Okay, or if it, if there are issues with the allocation. Should the allocator continue trying to allocate these pages even if so? You have one of two cases. One of them is basically, okay, I try to allocate, there is plenty of memory, I'm just getting the page. The other one is, oh, I do not get the page, I should repeat and try to reallocate once some of the pages are cleaned. No fail basically is like repeat forever, okay. So the allocation cannot fail. This is you're allocating something internally for the kernel, and this thing can never fail. And you can have it as well. You should never try this even, no matter what. I mean, you try it once. If it fails, you're not going to to retry the allocation. So there are multiple such options, and the mask, basically the GFP mask, is basically these are different bits. These are, each of them is a predefined bit, as we said in the struct of the that defines a page, and you can have all sorts of combinations between these. So instead of that, the kernel actually provides you with some flags that you can use instead of basically mixing and matching whatever you want. So I wanted to never retry, start the file system, can sleep, and compounds, add a compound page metadata. So there are like, for here's TLB basically. So I mean, you can have all sorts of these combinations. So instead, they provide you with some flags that you can just use, and if you use them, it will basically use the right masks so that you don't need to think about them, and allocate the pages as you wish. So basically, GFP atomic, the allocation is high priority, must not sleep, and this is what you would use in interrupt handlers, for example, in bottom halves, or while holding a spin lock. Okay, when you cannot sleep, basically. So you need a page, I have a spin lock, I'm an interrupt, I'm a bottom half, I cannot sleep. Okay, GFP no wait is like atomic, except that the call will not fall back on emergency memory pool, so it will not basically try to free memory for you to use. Okay, and this basically means that it can fail. The atomic will actually try to evict things from memory, will try to do all sorts of things. We'll talk about the emergency pools later and so on. Okay, no IO. I might be basically saying that, you know what, no matter what, you should never do IO in this. I need the block. I can block, but I should never do disk IO. Okay, this is basically what you should use in block IO code when you cannot cause more disk IO. Okay, because you might end up basically, so if you're doing disk IO and you need memory for that disk IO, and so basically, if you're, let's say that you have an in-memory cache and you're trying to fetch some data from disk, so you already start an IO operation, and or you're already going to start an IO operation, and to store that data you need some pages on your memory. So what you end up doing if you basically enable the system to call IO again is that if it doesn't find memory, it calls IO again, and then another IO operation starts. Now you need to handle this IO operation, get it into the memory, but well, I cannot basically find memory because memory is constrained now, so I start another disk IO because I'm trying to push things from memory to disk and back, so I can end up with a recursion that never ends, and I can end up with a loop that is crazy. And there are many such flags that you can use when allocating your memory pages internally inside the kernel. So now we have talked about how we actually allocate pages using the alloc pages, these calls basically, the alloc page, alloc pages, and get free page. Similarly, we need to talk about how to do free pages, and the kernel provides you with three main functions. One of them is __ free pages, that takes a pointer to the page, okay, and how many pages you're going to actually, so the order of the pages that you're going to free after this page, okay. The second one takes an address to the page, not a pointer to the page. The third one takes an address to a single page, and it removes a single page only. Now, you must be careful to free only pages you allocate. You're the kernel. You're writing code in the kernel. Okay? So you have absolute power to free any pages in the kernel memory, including, for example, freeing pages that the kernel actually uses, that the internal kernel uses. You can even free your entire task struct, right? So basically, killing your internal kernel. So if you're writing kernel code, you should not be basically, you should only free pages that you have allocated, not somebody else has allocated. And you should not go and try to free all pages or allocations in different areas unless you know what you're doing. Obviously, you're the shutdown command or something and you're freeing memory. So make sure that you never corrupt your data by just shooting yourself in the foot. Okay? So this is an example of how you would allocate pages and deallocate them. So you basically unsigned long page, and basically you because you're getting the page address, so you initialize the variable, and then you get the free pages. You say that it's GFB kernel, so you use that flag, and you say that you need 8 pages. Okay, 2 to the power 3. So if you do not get a page, if not page, so if the page is still not defined, then you have insufficient memory in your system and you must handle this error. Okay, and you return no memory. If you have a page now, if page basically, page is now the address of the first of the 8 contiguous pages. Okay, you start basically doing all sorts of things that you need: writing, reading, playing with your pages, and once you're done, you free the pages by just passing in the address and the order how many pages you need to free. Now, all of this we have been talking about allocating whole pages, but in many cases you do not need a whole page. You rather need some small memory, right? Maybe 1 kilobyte of memory. So in that case, you use kernel malloc or vmalloc. Okay, and kmalloc is used if you need physically contiguous memory. Okay, which is mostly something that you would need when you're dealing with hardware devices, when you're doing the allocations for hardware devices. And vmalloc is something that you use if you need virtually contiguous pages. Okay, contiguous memory. Sorry. So the way that you use it is that you give it the size that you're going to need, and you give it the same flags that we discussed previously when we were talking about alloc pages. Now the function returns a pointer to a region of memory that is at least the size in bytes. So so basically you can ask for 1 kilobyte, 10 kilobytes, 15 kilobytes, whatever. Kernel allocations always succeed. Okay, unless there's not enough memory. Okay, and in that case you'll get null, and you need to handle the error appropriately. There is a counterpart for kmalloc and vmalloc, which is k-free and v-free, and in that case you'll just call it with a pointer to the page that you created. Okay, in the kernel, since vmalloc actually is used to assign only virtually contiguous memory, it's less performant than kmalloc, because pages that you get from it basically can be all over the page table. So you use kmalloc to get better performance. We now turn our attention to another major difference between how the Linux kernel design and Linux and many other systems, and this is the slab layer. The slab layer acts as a generic data structure caching layer. So the idea is very simple. When you assign memory using kmalloc, for example, and vmalloc, you might have assigned the memory for using it for something specific, but now you have that memory and you start doing data using it for handling data. You no longer need it for the data for this data, but since the allocation has already been done, maybe you can reuse it for something different. So most kernel programmers used to introduce free lists in their code. This is basically memory that was allocated for a data structure and the data structure no longer exists. But instead of basically using v-free or k-free, the programmers basically decided that, or many programmers, what they do is that they have a list of free memory pages that they can reuse. So rather than allocating the memory, the free list has basically is a long list of whatever memory that was allocated already to your process, and that you can use for another data structure. It acts like an internal caching layer in the kernel for the different processes. It can be problematic when the memory becomes scarce, because basically each process is holding a list of pages that it's not really using. So it might be all of these pages can be basically, the entire memory can be free. Nobody's really using it. Still, since you have, you keep it as a reserve basically for future usages, you end up basically messing up your memory allocation by just having all your entire memory free, but no one using it. So to enable the kernel more control, the kernel provides the slab layer for all of these sorts of free memory lists. So you have a huge free memory list instead of multiple free memory lists. And now kernel programmers should never do the free memory lists again. It is implemented in slab.c, and the definition is in slab.h. There are some basic tenets for the slab layer. First, that frequently used data structures in the kernel tend to be allocated and freed often. So basically, let's cache them. Frequent allocation deallocation can result in memory fragmentation. So let's basically keep whatever allocation we got first for as long as we need. This is especially important when you think about how the kernel has been dealing with very small memory systems. To prevent this, the cached free lists are arranged contiguously. So basically, when you use the slab layer, you want to make sure that, well, it's sort of a cache of memory allocations that is contiguous. Because free data structures return basically to the free list, there is no resulting fragmentation. The free lists should provide improved performance during frequent allocation deallocation, okay, because basically you do not need to do a memory walk, or you do not need to get memory allocated. In reality, you're just like using memory that has already been allocated. If the allocator is aware of concepts such as object size, page size, and total cache size, can make actually much more intelligent decisions, because now you know that there are 10 pages that are already available. So maybe I can basically use these 10 pages in a much more intelligent way than just trying to allocate new memory. Now there are some things where the slab layer are actually very useful, and these are architecture dependent. One of them is that if part of the cache is made per processor, so separate and unique to each processor on the system, allocations and frees can be performed without an SMP lock. So you basically, it reduces the locking, because if the slab layer is per processor, then you do not really need to think about what other cores or what other processors are doing with the memory, because, well, this memory has already been allocated to my processor, so it's my processors, and since my processor never freed it, so it exists for whatever is running on my processor now. If there's NUMA architecture and NUMA architecture systems, and please go back to your hardware class for that, you can actually fulfill allocations from the same memory node as the requester, so you do not end up going to another memory bank basically. And stored objects can be colored to prevent multiple objects from mapping to the same cache line. Memory coloring is we're not going to go into these details. So what is the slab design? It looks like that. Okay. The slab layer divides different objects into different subgroups. Each one of them is called a cache, and each cache is divided into multiple slabs. Okay, and each slab is divided into objects. There is only one cache per object type. Okay, and basically, for example, you will have a cache for process descriptors. Okay, so a free list for task structures. You'll have one cache for network for network buffers. Okay, or for memory that deals with network buffers. You'll have one cache for the different kinds of objects that exist in your system. Kmalloc is actually not implemented on top of Slab. So Kmalloc does not try to get you memory from the physical memory. It actually tries to start an optimization. The optimization that it does is that it actually tries to get the memory from the Slab layer, memory that has been already allocated. And this basically enables Kmalloc to be highly performant. And basically, each object has the data structure is basically the data structures that are being cached, and each slab is in one of three states: full, partially, or empty. Okay. So basically, on the full, partial, or empty part, if your slab is marked as full, this means that, well, all the objects in the slab have been taken. So it doesn't make sense to try to allocate there. The kernel actually tries to use the partial slabs first, okay, and then starts. So the way it goes is that you never touch the full slabs. Never try to allocate memory into the full slabs. You try to allocate memory in the partial slabs. If you have no partially filled slabs, you then start filling the empty slabs. Now, if you have nothing in the empty slab, no empty slabs, then you try to allocate new memory. Historically, the kernel stack was actually preset to one page. In the beginning, it was set to 2 pages, 2 normal-sized pages, basically 2 4 kilobyte pages or 2 8 kilobyte pages. Then somewhere in the middle, basically people started saying that having 2 pages for a kernel stack actually hurts performance. So they started making it a single page that is a little bit larger than the normal page. So an 8 kilobyte page on a 32 bit architecture, and a 16 kilobyte page on 64-bit architecture. But historically it was non-dynamic. Okay, so the stack was non-dynamic. However, since 2016, new approaches have been suggested, including the virtually mapped kernel stacks. So if you're reading this part in the book is obsolete actually. The kernel does have methods and mechanisms to actually enable the stack to not be as rigid as it used to be. So now it can be dynamic actually. So if you're reading the book, this part is obsolete now. And this is a very interesting link on how the virtually mapped kernel stacks started. You'll find lots of material on lwn.net that actually discusses this addition to the kernel. So now we have complicated things a lot, right? Now how does the slab, how does this go with my page tables, that goes with my user space memory, that goes with my virtual memory, and so on. And now basically if you're looking at the entire memory subsystem in Linux, it's actually very complex. I actually borrowed this from a presentation. So this is a link to the entire slide deck. So basically you have kernel dynamic memory and you have user space memory. Okay, you have slab, you have the body system allocator. The body system allocator is basically your page tables, okay, or your the system partially your page tables, or what manages memory as in Linux and as the way you have studied in your undergrad courses. And you have the physical memory, and this is how the system looks right now. So you have the all physical memory on the left, okay. We're now ignoring zones, NUMA, and so on. So you have page memory, and you have kernel code and static data at the bottom, okay. And then you basically use you have on the right hand side the users of the memory, which is the kernel, and the user space memory. Okay, user space memory has the environment, then the stack, then the shared memory, then the heap, then shared libraries, then the code. Okay, while kernel memory has the kernel dynamic data and then the kernel module code segment. These are basically the kernel data structures that exist for different kernel processes and the code of the kernel. So you try to get memory using vmalloc or kmalloc. Actually, it's even missing here kmalloc. So there it's even a more simplified figure. So in the kernel, you try to get memory using the vmalloc or kmalloc, okay, which actually tries first to get it via no, actually kmalloc is here. It actually goes to the slab allocator. I'm sorry, just doesn't have a box. So you have kmalloc that goes to the slab allocator. The slab allocator either returns memory that can be used, or well, we have no more memory in the slab, so we go to the body system allocator, which basically is sort of the entire memory management that has been discussed with paging and so on, from physical to virtual to physical translation and so on. So you try to get memory from the body system allocator, and the body system allocator uses the virtual memory management component to actually get to the actual physical memory, okay. And that's the direction for the kernel data, and then the kernel data ends up in the bottom part of the memory. Now the user space memory is more interesting, because what you're going to do is that you're going to call the memory allocation function, and then this memory allocation function will go via the body system allocator, and the body system allocator will do the virtual to physical and physical to virtual memory handling, and then it will assign memory on the page memory. So it's a fairly complex system with lots of details, and this is actually even more simplified than what actually happens in real life. So basically, memory architecture in Linux is very, very complex. This is basically what you can take from this. Now, we have been talking mostly about the kernel space, except for when we were discussing this figure. So let's talk about the process address space, basically. The address space layout is mostly determined by the application or determined at compile time. So link directives can influence this. Operating systems usually reserves part of the address space to map itself, which is the upper DB on x86 Linux, or basically in this figure, it's like the bottom part. It's the upper DB because we go for memory from top to bottom. Applications can dynamically request new mappings from the operating system or delete mappings, and basically dynamically asks the kernel for anonymous pages for its heap and stack. The application has no clue what's underlying, so it's basically asking for memory, and that is all that it understands. So now the kernel needs to use take these requests and honor them and provide the application with the required memory. and this can entail basically swapping, because the memory is full. Lots of applications are using parts of the memory. This can entail basically evicting some unused memory. This can entail fragmentation, fragmented different memory pieces. I mean, to the application doesn't know any of these underlying details. It just knows that it needs this much amount of memory. You can actually take a sneak peek at the memory layout for some applications, especially using the LDD command, which prints the shared libraries required by each program and where they are in the memory. So basically, what does the ls command require? It requires Linux VDSO, but also it requires libc, and this is basically where libc is, and this is where the memory address of the shared library is. So basically, these are all shared libraries, which if you look at this graph, if you look at this figure, it's the shared libraries that are above the code and the user space memory. So there are different virtual memory areas, and Linux represents portions of a process with a virtual memory area struct or a VMA. Sorry about the break. So before we talk about the VM area struct, let us look at the different process memory areas that exist. For example, you have a memory map of the executable files code, and this is usually called the text section. You have a memory map of the executable files initialized global variables, and this is called the data section. A memory map of 0 page containing all uninitialized global variables. This is also called the BSS section. A memory map of 0 page used for processes user space stack. So you start with stack. An additional text, data, and BSS section for each shared library, such as the C library and the dynamic linker. These are basically the things that we looked at with the LDD command. Any memory map files, any shared memory segments, any anonymous memory mapping, such as those associated with malloc. So this is basically the different parts of the memory areas for a process. So Linux represents portions of a process with the VM area struct or VMA, and this includes its start address, its end address, and the protection of this area. Now when we were talking about the kernel memory, we did not talk about protection. Here we need to consider protection. In the kernel can access any part of memory in any way it wants, right? But now in the virtual when we're talking about user processes, protection becomes important because not all users will have write, read, execute access to the different memory areas. So basically, the VM area struct enables, or the VMA enables, the kernel to actually look at this, and the start address, this virtual start address, the virtual end address for each VM area of a process, and basically enables protection for each of these areas. Because for the same process, for example, you might have different protections for different parts of the memory. The memory types, the VM area struct is defined in mm_types.h. Now, the kernel represents a process's address space with a data structure called the memory descriptor, and this basically contains all information related to the process address space. So you have the VMA for certain parts of the memory, for certain areas of the memory, and then you have a data structure that basically has everything that is related to this process. and this is called the mm_ struct. Okay, again defines defined an mm_ types.h. It's very well documented in the code, so you can take a look. And the memory descriptor associated with a given task is stored in the field of the task process descriptor. You can look at the field there to basically see where in the task process descriptor and the task struct, basically you will find an field that basically links to the struct struct over here. Okay, now there are lots of complications with the user process with the address space and the process address space for users. I have chosen to actually cut a lot of the descriptions here. A, because a lot of this is common with Linux. B, because some of them are very deep details. So for example, searching searching the between the different memory structs and how to find data between the different virtual memory areas and between the and how does it link to the struct is really something that you will probably never use in your entire life. And the design is in many ways well, I'm not going to say complicated, but convoluted. So it's basically I didn't see a lot of value into adding these details to you guys. The page cache and page write back. This is actually an important part which of the memory system. It's actually somewhere between the memory and the file system. And the page cache is the idea is that RAM is orders of magnitude faster than disk. So the page cache consists of physical pages in RAM that actually map to physical blocks on a disk. Okay, so the idea is that you read from disk, store it in RAM, and or store it in memory, and basically use these pages instead of writing and reading to the disk directly. The size of the page cache is dynamic. It can grow to consume any free memory and shrink to relieve memory pressure. So basically, in many occasions, if you're reading a huge file, for example, a huge text file, but you're at the same time running heavy processing or running an in-memory database where everything is just in memory, or running some processes that are memory bound, then the page cache can increase or decrease based on how much empty memory, how much free memory exists. The storage device that is being cached is called the backing store, because basically it stands behind the cache, and the cache is trying to reflect the reality of the backing store. So it is the canonical version of the cache data. Basically, it is the true version of the cache data. Entire files are usually not cached. Some files would be entirely cached, but it does not need to be that way. It depends on what parts of the file you're actually accessing. So this is actually something to keep in mind. So now you are reading and writing from this file. Reading is fine because you are not changing any data, but writing to a file requires that you change whatever is in the cache. And there are one of three strategies to write to a cached version of a file. The first one is that you do no write, and that basically means that you write to the stored file on disk, and when you do that, your cache gets invalidated and needs to be repopulated from disk. So all writes do not go to the cache, they go to the disk. Now this comes at a large cost, because what you're doing is in reality you're going to be invalidating your caches often if you're writing a lot, and you're going to be writing to disk directly, which actually can mean that it takes time and to write to disk basically, so you can have delays and performance issues. And in addition, you can have very weird consistency issues. So write through cache is another way, is another strategy where what you do is that whatever you write to the disk, you write to the cache in parallel. This basically makes your cache coherent all the time, and is quite simple because you're going to write to both. However, it comes at some performance costs, as we'll discuss in the third strategy, which is write back, which is the default policy in Linux. The write back caching policy requires that you write first to the cache, so everything gets written to the cache and does not get written to the disk. The reason that you're doing that is that, as we said, disk seeks on HDDs. Now these numbers would change with newer hard disks, SSDs, but many hard disks are still HDDs, which basically means that there is this there is a spinning real motor that actually needs to spin physically to go to the sector which you're going to read. So this, if you're writing often, this comes with quite a large cost in terms of seek time, and it can actually result in thrashing in your performance. So the way that write back caching works is that you write to the cache, and once you have sufficiently large amount of data to be written to the disk, you start writing them. Now, there are a couple of things that one should mention here. One of them is that you cannot wait for too long, because if your computer restarts and you take too long to actually cache, write the cache, then all of the data that you have written will be lost. So there's a fine line between how often you write to the actual disk and how you actually do the collective writing. And this comes back to our discussion of dirty pages when we were talking about the different flags for the struct page, and one of them was that it can be dirty. And here, dirty means that it goes to a dirty list, and there's a full dirty list of pages that the kernel needs to write back to the backing store. Once the disk is done with basically copying, or once the kernel is done with copying the data from the dirty pages to the backing store, then what happens is that these pages are no longer dirty and this flag is changed. Write is thus performed in bulk, optimizing access to slow disks, and applications can force immediate write backs with a sync system call. So you can actually force your system, if you're writing your program where you think that I should be forcing my system to write now, you can do that easily using the sync system call. The Linux page cache is basically a page in the page cache can consist of multiple non-contiguous physical disk blocks, basically. So you might have them from different parts, okay? And before you try to do any page IO, you check in your page cache, on your Linux page cache. The overhead of searching and checking the page cache, however, could nullify the benefits from the cache, because if you have different pages that are all over the memory, okay, and and you need to search a huge page cache multiple times, it can actually invalidate and nullify any benefits from having the cache in the first place. So some parts of this search is implemented as an efficient radix tree. Cache reclamation. Kernel caches and processes can continue assigning memory basically for as long as is needed. Okay, so you basically start considering cache reclamation when you hit a wall, and hitting a wall happens when you have low memory, if you're going to hibernate, if you have a free memory target that you should have, but you all of a sudden have less than that much amount of memory. Memory pages can be divided into one of four categories. The first one is unreclaimable. So these are free pages that you cannot basically reclaim. For example, pages pinned in memory by process. Sometimes you can do page pinning by process. Some pages that are locked, you cannot reclaim them, and some kernel pages. Swappable pages are pages that are like anonymous pages that were requested by the user space. These can just be swapped to disk, for example. There are other kinds of pages that can be swappable also. Then there are syncable pages, and these are cached disk data. And in that case, to reclaim these pages, all you need is basically to either reduce your cache size, okay, and keep smaller amounts of data in your Linux cache, or maybe looking at dirty pages that have not been used for a while, writing them. I mean, there are multiple different ways to actually reclaim syncable pages. And discardable pages, and these are pages that have been not been used for a long while in the cache allocators. Cache eviction policies, there's the least recently used, which you probably have covered multiple times now in this course and in other courses. The Linux way is that it has a two-list strategy. It's actually like a least recently used two-list or two-list approach. So the two lists are basically an active list and an inactive list. The active list are pages that are hot, pages that are touched, pages that are not available for eviction. Okay, and the inactive pages are pages that can be cache evicted. Okay, pages are placed on the active list only when they are accessed while already residing on the inactive list. So pages start on the inactive list, and then they move to the active list when they get read, for example. And Linux tries to keep the two lists in balance, so that your bottom list has the half of all the pages that you have not accessed, or the least accessed pages, basically taking the medium page and taking all pages below that page, and saying that these are the least accessed pages, and then the top list, which is basically the hot list or the active list, and this is not this is not evictable. This approach is also known as LRU2, and it can be generalized to N lists with LRUN. With this, we conclude today's lecture on memory management. The next lecture will be the last lecture in the course, and it will be on file systems.